Good afternoon, everybody. I should have switched to this view here. Yeah, good afternoon, everybody. This is a Calculus 1, and this is intended to replace a class that's happening on Tuesday, September 16th. I will not be in class, and so I don't expect you to go to class either, but I do expect you to watch this video and to take notes and to do all the usual things that you would do if this was an in-person class. In particular, make sure that you are formulating questions, thinking about comments that you might have about the material, and then posting those to a discussion forum that I'm going to be setting up. I'm going to set up a discussion forum that I'm going to call Quiz Number 3 Preparation. What's quiz number 3 about? That's happening on Thursday, right? On Thursday of next week. That's September, I think 18th. Yes, September 18th. We're having a quiz, and this quiz is going to be on the material that is covered in these two video lectures. The one that I'm going to create right now, and the one that I did yesterday. Okay, so watch those, make sure you understand. To test yourself in FIRE, there is also a web work assignment, which is somewhat beefier than previous web work assignments, so make sure that you get a jump on it. But I think it should be relatively straightforward if you understand the material really well. There are a few curveballs in there, but that's okay. You're not children, and you can handle it. But if you really understand the material, okay, it should all be accessible to you. That's the feeling, at least, that I have right now. Yesterday, right. Oh, right. And if you have any questions about that web work assignment, please feel free to post in the discussion forum about it. And if you do post in that discussion forum, either post a question, a comment, a reply to a question, a reply to a comment, I'll give you 2% extra credit for quiz number 3. By the way, I made the same offer for quiz number 1, and I realize I haven't recorded that data yet. Rest assured, I will do that. And I'll be looking for people who posted before the deadline. The deadline for the discussion forum submissions, we'll call it Thursday morning at 7:59 a.m. So if you post right before class, you might get in just before the deadline. What else to say? Well, I don't know. Yesterday we talked about a few things. Let me switch to this thing here. Yesterday we talked about, just as a quick review, well, the definition of the derivative as at a point, but also the definition of the derivative as a function. We talked about the cases where f was a constant function and where f was a linear function. And remember, every constant function is a linear function where m is 0 and b is equal to whatever number the constant function is equal to. And then I proved, of course, that the derivative of a linear function is equal to just the coefficient in front of the x term, m in other words. I proved this using the definition of derivative, neato. And that implies, of course, the results about constant functions. Then I mentioned, or I said out loud, the power rule. Here it is. You should really get to know this one because we're going to use it all the time. But I did not prove it. I did not justify it. So this should leave you in a kind of shaky situation where you don't necessarily know why this is true. And indeed, I'm not going to be justifying it in full generality until we get access to logarithms and talk about the derivative of those. And in order to talk about the derivative of logarithms, I need to talk about the derivatives of inverse functions, and I need to talk about the derivative of the exponential function, but that's all for later, future us, okay? Right now, I just want you to take this as given, as gospel. I'm not lying to you about this. This is completely correct. So you should just trust me on this for right now. You need not, if you're skeptical, I appreciate your skepticism. But again, I will justify it in full generality later. No, okay. But let's keep pressing forward with all of this stuff. And let me ask you, what I want to do for you is re-mention one of the things I talked about at the end, which is the constant multiple rule. Here's what it says. Here's the concise way I would describe it. If I want to take the derivative d dx of a constant times a function, f of x, which I might denote this state of affairs like this. Remember, this is operator notation. This is like the notation is saying, take the derivative of everything which is to the right. Take the derivative of a constant times a function. That's equal to the constant times the derivative of the function. And the derivative of the function, we have special notation called Leibniz notation for that. And so I'd write it like this. This is a concise mathematical description of the rule in question, the constant multiple rule. If I was to say this out loud, here's how I would say it. The derivative of a constant times a function is the constant times the derivative of the function. I know it's a lot of words in a row and you don't like reading, but if you read it very carefully, you'll see the way in which this equation is really a mathematical way of expressing this English sentence. And I swear to you, this English sentence makes sense, okay? I'm talking about the derivative of a constant times a function is equal to, or is, the constant times the derivative of the function. Is exactly, it tracks here. But what you notice, this is maybe an aside comment, is look at the word here, the derivative, and look at where it appears in the second clause, the derivative there, and look at constant times. Do you see that in the first clause? That is to say, the thing before the is. Like, look here. The derivative of a constant times a function. That's the first clause of the sentence. Notice that the derivative word comes first, and then the constant times word comes second. Whereas in the second clause, which is asserting that this is, and these clauses are supposed to be the same, right? Is, after all, is the connective. The constant times, that's the first thing that appears, times the derivative. In other words, it's like you can swap the order of these things. Taking the derivative of a constant times a function is taking that constant times the derivative of the function. If you say it enough to yourself, you begin to see how the position of the derivative thing and the constant times thing is swapped. Don't worry about that too much if you don't understand what I just said, but it's true. And so it might be helpful for you to think about. So this is like how I would say it in English. And it's always good to have an English description of mathematical things. Translating from one world to the other. It's like translating languages. Okay. So, like, let's say that we had the following situation. Example. Suppose f of x is a function for which f prime of 4 is known to be 7. I give you a function which has this particular property. Suppose g of x is a function, and g of x is equal to 9/5 of f of x. So in other words, g of x is a constant times this function. Then what is g prime of 4? The question is to find g prime of 4. And this is pretty easy now that we have the constant multiple rule. I haven't proved it, I will. But now if you believe the constant multiple rule, here is the solution to this problem. G prime of x, the derivative of g, okay, is the derivative of the constant times f of x. So I might denote this state of affairs like this. Well, I can use prime notation. And we should be fluid with these prime notation, moving between prime notation and the derivative notation. And what this is saying is that I'm taking the derivative of a constant times the function. The derivative of a constant times a function. And what the constant multiple rule tells me is that this is equal to 9/5. The constant times the derivative of the function. The derivative of f we can conveniently write as f prime of x. Now, this is a statement which is true for all x. So in particular, we want g prime of 4. So we now specialize to x equaling 4, and what we learn is, so g prime of 4 is equal to 9/5 f prime of 4. Do you understand how I did that? G prime of x we learned is equal to 9/5 f prime of x by the constant multiple rule. Now I plug in x equal to 4 and I get this equation. But 9/5 f prime of 4 is 9/5 of f prime of 4, which is 7. That's given to me. So this is 63/5, because 7 times 9 is 63. And that's the answer. Okay? So this is a simple way, a little bit more theoretical. Not theoretical is not the right word. Just a little bit more abstract than maybe some other examples that you're going to see. Because we're going to use this all the time. We're going to use it so much, in fact, that we're not even going to make mention of it. It's just going to be like a thing that we automatically do with our brains without even really thinking about it. Give me one moment here. Okay, looking okay. Looks good. All right. So now I want to prove it. I want to prove the constant multiple rule. Just so you see what these things look like. Constant multiple rule. Multiple rule. Rule. Colon. Of course, what I'm going to use is the definition of derivative. I'm going to start with the left-hand side here. So d dx of c times f of x. Okay. This is equal to a limit as h goes to 0 of c times what I get by putting x plus h into this expression. If I put x plus h into here, I get f of x plus h times c, right? And then I subtract off just the function itself, left alone. And then I divide this whole thing by h. Of course, the point is that we can factor out a c from this quotient here. This is equal to the limit as h goes to 0 of c times f of x plus h minus f of x divided by h. You can write it like this. If you're uncomfortable with the way this looks, you can put big old parentheses like that. That looks maybe a little bit better. But then the point is that I can take this c and I can move it outside the limit, because notice that this is just a number times some expression. And as h goes to 0, because the c does not depend on h, the limit as h gets closer and closer to 0 of a constant times something is equal to c times that, or that constant times the thing as h goes to 0. So this is just c times the limit as h goes to 0 of f of x plus h minus f of x divided by h. And this is just, look at what I've got here. This is simply f prime of x. And so we proved it, right? That's a synonym for that. Relax, okay? Great. That's the constant multiple rule. And again, it's going to be second nature. The more you practice with this stuff, it will not be something mysterious. You're going to use it all the time, and it's going to like be in your hand bones rather than in your brain. Let's also prove or talk about what happens when you take the sum of two functions. So the sum rule. Let's talk about this. So to be clear, before we get to the sum rule, actually, can we just talk about this before we state it? Let's talk about the sum of two functions. Okay? So if you have two functions, f of x and g of x, so suppose you have f of x and g of x are two functions. One's called f, one's called g. I really should write f and g, but whatever. Then we define a new function. Okay, I don't want to get too abstract. We define a new function which we call f plus g. Okay? This is a new function which eats as input x. So we're going to take this new function. Its name is f plus g. It eats as input x. And guess what its output is? It's f of x plus g of x. Very sensible. Very, very sensible. And by the way, you can define like any operation that you can do with real numbers, like addition is one, but there's others like subtraction, there's multiplication, there's division by a non-zero number. Any of those arithmetic operations you can also do to functions and define new functions from old using arithmetic. Okay? There's one other operation that you can do with functions that you can't do that is not arithmetic, that is going to be of a particular importance to us, and that's composition of functions. This is where you take one function and another function, you use the output of another function as the input to the function. F of g of x. Remember that? And there is a rule for taking the derivative of such called the chain rule, but that's for another day. For right now, we want to talk about what happens when you have f and g and you take their sum, f plus g. What is the derivative of f plus g? So this is the statement of the sum rule. Here's how I'll write it, maybe. I'll write it like this. d dx of f of x plus g of x is equal to f prime of x plus g prime of x. I'm mixing up notations. In other words, the derivative of a sum is the sum of derivatives. Do you hear how that's swapping again? I would say this out loud. The derivative of a sum is the sum of derivatives. This is a kind of a shorthand way of saying it, because sum of what? Derivative of what? But hopefully you can fill in the blank. This is how I'd say this out loud. And do you see how, yet again, in this case, we have the derivative here operation, the derivative there. Now we have a different operation, sum and sum, but again, we have this sort of swapping of the positions. Again, if you don't understand what I'm saying, just ignore that. But at the very least, I do want you to understand how this English statement is a concise description of what's happening here. On this side, we're taking, follow my pen, the derivative of a sum is the sum of derivatives. The derivative of a sum is the sum of derivatives. The derivative of a sum is the sum of derivatives. Okay. Let's prove this one. I don't know if I can, well, I'll fit the proof in right here. So let's start with this side, d dx of f of x g of x. Have I undermined myself a little bit? Oh, whatever. This is f of x plus g of x is, of course, f plus g of x. That's how it's defined. Okay, whatever. All right. And this is the limit as h goes to 0 of what I get by sticking x plus h into here. X plus h minus what I get by sticking just x into here, which is just f plus g of x. divided by h. But of course, we know what f plus g does to an input. It simply takes the sum of f eating the input and g eating the input. F of x plus h plus g of x plus h minus f of x plus g of x divided by h. Yes. Now, this is yet another moment where you are screaming at your screen, and I might, in class, do my gaslighting routine and ask you, is this okay? Is this okay? And then you say yes, yeah, oh no, etc., etc., etc. Okay, just play that out. Fast forward, bzz, and then realize that we are missing parentheses here because this minus sign is touching everything in f of plus g of x. And so we need parentheses like this to indicate that. Well, what's the point? I'm going to continue down here because I don't have much room. This is equal to the limit as h goes to 0 of now I'm going to rearrange terms. So this minus sign touches both the f of x and the g of x. I'm going to move the minus f of x next to the f of x plus h, like this. And then I have a plus g of x plus h. And then I'm having a minus g of x. So it's like I'm segregating the f bits from the g bits, like this. Now I'm going to break up this fraction into two pieces along this plus right here. We know that if we have a sum in a numerator, like if you have a plus c over b, right, then you can write this as a over b plus c over b. That's just a basic rule of arithmetic. Well, we can apply that here, splitting this fraction up along that plus. You see where my pen is? That plus right there. And rewrite this as the limit as h goes to 0 of f of x plus h minus f of x divided by h plus g of x plus h, oh gosh, minus g of x divided by h. And I really don't want to use another piece of paper for this, but it is true, I guess. You see how these are looking like the definitions of the derivative for f and g. The only thing I'd have to convince you of right now is that as h goes to 0 of a sum, this the limit of a sum is the sum of the limits. So this limit could get attached to this and attached to that there. Fine, I'll use another piece of paper. So there I am there. If I continue this calculation, I end up with the limit as h goes to 0 of f of x plus h minus f of x divided by h plus the limit as h goes to 0 of g of x plus h minus g of x divided by h. And the point is that this is f prime of x, and that is by definition g prime of x. Just the definition of the derivative. Where did that come from? It seems like such a leap. Oh, it came from the definition of the derivative. Remember? Where is it? Is it this? Where is the, oh, sorry. Where is the definition of the derivative? I have it on a piece of paper. Here it is. This is from yesterday. The definition of the derivative. And I'm just applying it to f here to get this, and to g here to get that. Great. Okay, so as an example of a calculation, okay, let's say that we had x cubed plus 1 over x squared. Okay, what is its derivative? So what if I wanted to take the derivative of this, prime all of this? Well, by the sum rule, this is equal to x cubed prime plus 1 over x squared prime. I don't love the prime notation because it looks exactly like a 1, and then you're going to call me a hypocrite again because I should just do something with my 1s, but whatever. X cubed prime is, by the power rule, 3x squared. Bring the 3 out front, decrement the exponent. This piece here we should rewrite first as a power of x. And we rewrite it as x to the negative 2. Now I take its derivative, I end up here with 3x squared. And then the minus 2 is going to come out front, so we're going to have a minus 2x, and then we decrement the exponent, negative 3. And that's clean and fine. If you don't like negative exponents, you can fix that yourself. I don't care. This make sense? And right, so the key sum rule moment was where we went from this expression to that expression, because we took the derivative of this sum and expressed it as the sum of derivatives. Okay? What if I was to ask you about the second derivative? So example, what is x cubed plus 1 over x squared double prime? That's not 11, that's prime prime, meaning that we're going to take the derivative of the derivative. It's called the second derivative. So the derivative of the derivative is the derivative of 3x squared minus 2x cubed. Oh, sorry. 3x squared minus 2x to the negative 3. My bad. Okay. But this, by the sum rule, is equal to the derivative of 3x squared prime. And remember that subtracting, like a minus b, okay, this is really a sum of a plus negative b. So even though we have something called the sum rule, okay, we can apply it to differences if we think of subtraction as being a sum. So here we can rewrite this as this state of affairs as plus negative this. So we get plus negative 2x negative 3 prime. You see how that happened? This is me using the sum rule, and I'm just going to point that out. Next thing, I notice that in each of these derivatives, I have a constant multiple, namely 3 times a function. In this first one, I have 3 times x squared. So I can rewrite that as 3 times, that I'm taking the derivative. So I can rewrite that as 3 times x squared prime. So here I'm saying, take the derivative of x squared only. Forget about the 3. Just move the 3 outside. And here, I'm going to take the negative 2, move it outside. So that's going to be negative 2 times x to the negative 3 prime. This is by the constant multiple rule twice. Now I use the power rule twice. So we have 3 times 2x. 2x is the derivative of x squared because I took the 2 down out front and decremented the exponent, but 2 minus 1 is 1, and nobody bothers to write 1 when it's a power. And over here, I get minus 2 times negative 3x to the negative 4. And this is the power rule twice. And now I'm going to clean up this mess here. So I have 6x there. And then I have plus 6x to the negative 4th power. Okay. So this is just, yeah, clean up. Now, I swear to you that in the not so distant future, you're not going to be writing out everything so explicitly. And I won't either. If I'm going to take the second derivative of a function, I'm going to write out the first derivative. I'll do that. And I'll do that kind of more or less in my head, honestly. Like, we will get so familiar with the sum rule, the constant multiple rule, the power rule, that we will be able to go from this line to that line more or less immediately. Okay? Similarly, we will be able to go from here, which is the derivative of this function, down to here, which is the second derivative of the function, just by recognizing what needs to be done. We need to use the power rule. Like, we won't consciously do it. We'll just do it. That's the level of sort of practice and fluidity that I want you to have with the derivative. Okay. How long? So I've been talking for 30 minutes. That's fine. So I proved the sum rule. Let's do another example. Let's just do lots of problems. Here's a question. Suppose f and g are functions, and let's say f prime of -2 is equal to 3, and g prime of -2 is equal to -8. Okay? I'm just making this up. Like, really, it's just off the top of my head. Okay? Let h of x be equal to -3 f of x plus 4 g of x minus minus 7/8. Do I want to do that to myself? Minus 7/8. Well, let's make it 7/8 x. Okay, good. So h is a new function which is built out of f and g. Okay? Here's my question. What is h prime at -2? Yeah. What is it? So my recommendation is that you first answer the question, what is h prime of x? That is to say, like, forget about -2 for a second. Can we rewrite h prime of x in some way? And then after we find h prime of x, plug in x equal to -2. So first go general and then go specific. Does that make sense? So if I continue this calculation up here, okay, forget about this. This is an aside. Solution. Let's look at h prime of x. So this is the derivative of all this mess down here. Sorry, you see, I'm down here again. Just deal with it. You have to take the derivative of all this down here. So that's the derivative of, and I'm going to, sure, can I use Leibniz, please? I'm going to use Leibniz. d dx of this whole mess here. -3 f of x plus 4 g of x minus 7/8 x. Now, you might be saying to yourself, geez, okay, I'm taking the derivative of a sum of 3 things here. And you're right. But the sum rule was only applying to the derivative of a sum of 2 things. And you're right. But if you like, you can think of it like you're going to take the derivative of just this piece, and then take the derivative of the second piece being these 2 pieces together. But the derivative of these 2 pieces together is simply the sum of the derivatives of these. So it turns out that, again, the idea that the derivative of a sum of many things is the sum of many things, the derivative of a sum of many things is the sum of those many things, each of which we take the derivative of. Bottom line, this is equal to d dx of -3x, 3f of x I mean, plus d dx of 4g of x plus d dx of -7/8 x. Please make sure you understand how that happened. It's well within your grasp. You can. And that's the sum rule. Next, I'm going to use the constant multiple rule. Pull out the -3, pull out the 4, pull out the -7/8. So this is -3 times df dx. You agree? This one is 4 dg dx. And finally, we have -7/8 times you write dx dx, but the way I'm going to think of it is d dx of x. And what is the derivative of x? That's 1. What's the derivative of f? Well, I'm going to I'm sorry. I'm going to go back to the f prime notation that I used over here. So df dx is just negative 3 times... this is just f prime of x. And dg dx is just g prime of x. And d dx of x is just 1. That's by the power rule again. Sorry, I don't know if I remember talking about this. If you have d dx of x to the first power, by the power rule, we're playing with the power rule where r is equal to 1. So we put the 1 out front. We take x and raise it to the 1 minus 1 power. That's me literally using the power rule. 1 minus 1 is 0 in this universe. So this is equal to 1. And nobody, by the way, nobody writes 1 times. You just write the thing. You don't write 1 times the thing. X to the 0. X to the 0 in this class is 1 for all x. Including x equals 0? 0 to the... Yes, it's 1. Real? Yes. Okay, good. So in particular, I could have said this in a different way too. Not with the power rule. I could have used the linear functions rule, right? Because x is of the form mx plus b, where m is 1 and b is 0. And then f prime is just 1. Okay, I could have done it that way. That would have been easier. What we get here, minus 7/8. Okay. And so what we learn is that h prime is all this mess here. Feel it? So in particular, h prime of negative 2, which is what the question is asking for, is equal to negative 3 times f prime of 2, negative 2 I mean, plus 4 times g prime of negative 2, minus 7/8. Cool. Oh yeah, and we're given the value of f prime of negative 2. It's 3. And we're given the value of g prime of negative 2. It's negative 8. So this is equal to negative 3 times 3 plus 4 times negative 8 minus 7/8. And this ends up being negative 9 minus 32 minus 7/8. And now the hardest part of the problem is the arithmetic, which is, this is negative 41 minus 7/8. And if we care, we have to write this as a single fraction. So we need to know how many eighths 41 is. So that's 41 times 8 eighths. 41 times 8 is 328. This is negative 328 over 8 minus 7/8. And if you do the math, that's negative 335 over 8. The arithmetic, I mean. Yeah. There it is. We did some delicate work with notation and such. It's a little kludgy, okay? I have to admit. But this is how I legitimately think about it. And I swear to God, everything here makes sense. I'll just say it like that. Like, I know I'm flipping between the Leibniz with the prime notation and all of that. And that is happening. But what is that on me? I don't know. But it's correct as written here. All right, great. One last thing I want to talk about, and this will be useful for your homework. We'll talk about lines for a second. And I don't want to go into huge long excursion into this. I'm just going to state a fact that you can believe or not. If you have a line of slope m, so suppose that you have a line, not a lime, a line of slope m, okay, in the plane, and let's say that you have 2 points, and x1, y1, and x2. Actually, let me just say it like this. Sorry. Let me do this a different way. I don't like what I just did there. Let's do this differently. So let's say you have a line of slope m and a point. And I'll call this point A comma B, lying on the line. Okay, so I can draw a picture, obviously. Lines are pretty geometric, so I can do this. So here is a line of slope m. By the way, that's negatively sloped. Imagine that. And we have a point lying on the line. Call it A comma B. Okay? Its x coordinate of that point is A, y coordinate is B. Question. What's the equation? What's an equation of the line? So, in other words, and when I say an equation of the line, I mean something specific. I mean an equation involving x and y, because this is in the xy plane, an equation in the xy plane involving the variables x and y, so that anytime you have a pair x comma y which satisfies the equation, that point will live on the line. This is the link between geometry and equations. An equation determines a line if the solutions to that equation are points that live on that line. Does that make sense? So, the reason why I write an equation as opposed to the equation is because there isn't the equation. There isn't just one, generally. There's many, many possible equations for a line. Let me give you one way in. So let me say it like this. Suppose we want x comma y to live on the line. Okay, so now I'm imagining a general point. I'm given AB, but I'm now imagining some other point. Maybe call it x comma y. Maybe that lives way up here. Okay? Just imagine. Then what I can do is compute the slope of this line by looking at the difference in y coordinates and the difference in x coordinates. I know that m is equal to the difference in y coordinates, so that's y minus b. And then I look at the difference in x coordinates, that's x minus a. Okay? And it doesn't matter what x and y are here, as long as, of course, as x is not a. So I guess we suppose we want x comma y to live on the line, and xy is not equal to ab for just a moment. Okay? Because if it was, then we'd be dividing by 0 in this slope calculation. But just relax, okay? All right. Now what I'm going to do is multiply both sides by x minus a. So, and I'm going to write it in the other order because this is the one I'm comfortable with. Y minus b is equal to m times x minus a, like this. So all I've done is multiply both sides of this equation by x minus a to get here. And then I wrote it in the other order for reasons that are mysterious and known only to me. And now I'm going to add b to both sides. Sure. This is an equation for the line. The line of slope m passing through a comma b. What's the logic here? It's starting from this realization. This is the rise over run idea, right? Rise over run, if you like, or if you don't like stupid things like delta y over delta x. Yes, the change in the y coordinates divided by the change in the x coordinates. That's what we know the slope to be. And using the formula for slope, we can arrive at an equation of the line in these general situations. Okay, Now I have 5 minutes to explain something to you. Recall that if y equals f of x, that, let me say it differently, that the tangent line to the graph y equals f of x at x equal to a has slope f prime at a. In other words, we compute the derivative of f and we plug in x equal to a into that derivative. And that's the slope of the tangent line. So this is now thinking about a situation like this. We have the graph of our function like this, yeah? And then maybe this is our particular point at x equal to a. And then here's our tangent line. And what I'm saying is that if this is the graph y equals f of x, then this point here corresponds to x equal to a, then the slope of this line is f prime at a. This is the setup for the derivative, right? We know this. Question. Look at this green line. Do we know a point which lives on this line? Yes. Which point? This point right here. You see the tip of my pen? That point. And what are the coordinates of this point? Well, the x coordinate is a. What's the y coordinate? Well, because it lives on this graph of given by y equals f of x, we can plug in x equal to a and we get the y coordinate out. It's f of a. What I'm saying is we have exactly the data that I've listed here. We know the slope of this tangent line in this setup, and we know a point which lies on this line. And so we can, in principle, use this to write down equations of tangent lines. Let me give you an example. So let's take, suppose f of x is equal to x squared minus 2x plus 5. Okay. What is the equation of the tangent line? What is an equation? Sorry, not the. An equation of the tangent line at x equals negative 2. Sorry, you can't see that. Ugh. Better? Oh, now you can see my legs. Great. Whatever. Who cares? Yes? Okay, so then we first take the derivative of f. Oh, okay, right. So the graph of this is going to be a parabola, okay? And what we're interested in is what's happening to the tangent line at x equal to negative 2. So following this idea here, we're going to first compute f prime of x. We do this by repeatedly using the power rule and the sum rule and the constant multiple rule. Here's how I think about it. The derivative of this piece, x squared, is 2x. The derivative of this piece here, negative 2x, think of negative 2x as being a linear function, if you like, where m is negative 2 and b is 0. The derivative of negative 2x is minus 2, negative 2. And 5 is just a constant, so it dies under the derivative. So we get this here. F prime of x is equal to negative 2. 2x minus 2. Cool. Now let's evaluate. So the slope of the tangent line is what am I doing? Sorry, is f prime. I'm feeling rushed. F prime of negative 2 because I want to get this under 50. And now we just plug in negative 2 here, and we get 2 times negative 2 minus 2. That's negative 4 minus 2, which is negative 6. Okay. So now we know the slope of the line. This is what's playing the role of our m here. We also need to know a point on the line. Well, as we said, the point is given by a comma f at a. So this is given by a, and a in this case is negative 2. This is given by negative 2 comma f at negative 2. Negative 2 is negative 2, but f of negative 2 we can compute. If we plug in negative 2 into here, we get negative 2 squared minus 2 times negative 2 plus 5. And now we do some calculation. Gross negative 2 comma 4 plus 4 plus 5. 4 plus 4 plus 5 I think is 13. And I know I'm 1 minute over, just relax, okay? And now we can use this form, if we like, to write down the equation of the line. Y equals then m, which is negative 6, times x minus a. What's playing the role of a here is negative 2. So that's x minus negative 2, which is x plus 2, plus b. B is being played by 13 here. Oh, and don't be weird. Okay, that's b is not the same. Fuck. That b is not the same thing as the y-intercept. Yeah, whatever. It's just not. I wish I had chosen a different letter at this point, but it's too late because I'm not remaking this whole video for that. So I get this. If you do want to know the y-intercept, of course, you can goof around with this to get it into y equals mx plus b form by distributing the negative 6. Another way of writing the same thing is negative 6x minus 12 plus 13, which is plus 1. Here's what I want to say. Either one of these is acceptable. Why? Because I asked what is an equation, and either of these is an equation for the tangent line. So you don't need to provide both, just provide one or the other. Okay, that's enough. Good luck on your homework. You'll have questions about this tangent line business, and we'll have occasion to talk a little bit more about all of that. And be thoughtful, okay? If you have questions, put them on the discussion section thing, the discussion forum thing, and hope to see you soon. Hope you are all safe and happy and all of that. And see you on the 17th.